Welcome to Lecture 10, Introduction to Sequences of Numbers. Let's start by introducing these two terms. Definitively and frequently. Now, of course, we know these two terms from the common language, but as we will see, these two terms have a different meaning in mathematical analysis. Let P of n be a predicate with parameter n, natural number. So P of n is a predicate with a parameter n, which is a natural number. Then we say that P of n is definitively true, and we often say just def if P of n is true from some n0 natural number onwards. In symbols, we can write that there exists at least one n0 natural number such that for every n larger than or equal of n0, P of n is true. So this is the definition of the adverb definitively. It means that some predicate is true as long as n is larger than or equal some n0. We then define P of n. We say that P of n is frequently true, and we just say FR if P of n is true for infinitely many values of n. In symbols, we say that for every m into the natural numbers, there exists at least one n larger than or equal to m such that P of n is true. So this is the definition of frequently true for a predicate. A predicate is frequently true if it is true for infinitely many values of n, which not necessarily means that this is happening very often. In fact, as an example of this, let's consider the case where some predicate P of n is true if n can be expressed as a power with the base 2 and exponent in turn to be another power of 2. So 2 raised to the 2 to the k for every possible k in the natural number. Now, this doesn't happen very often. It doesn't happen very often that a natural number can be expressed in this way. Still, we can say that P of n is frequently true, because this happens for infinitely many values. Okay, so we are ready now to give the definition of sequence. And we'll give two definitions of sequence. A formal definition and then one that is more commonly used. So the formal definition is the following. A sequence is a function f from the natural numbers to the real numbers. Examples: a of n. This is just a way of representing a function of a natural numbers that takes value in the real numbers, but most commonly we use just a with the subscript n, equal to, well, for example, n to the square plus 3, so that if we want to evaluate a of 0, well, this is just a0 is just equal to 3. Instead, a1 is equal to 1 to the square plus 3, which is equal to 4. a2 is 2 to the square plus 3, which is equal to 7, and so on and so forth. Another example is bn equal to 1 divided by n plus 5. Right, so this is the formal definition. For every possible natural number, we have f defined in that natural numbers. But the common definition is the following. Is basically it is based on the observation that fn does not need to be defined for every natural number n, but it is sufficient that f of n is defined is true, let's say, is true definitively, which is just like saying that there are only a finite number of problems in its definition. And now let me give you some examples. If we say that an is equal to 1 over n, well, clearly this is defined for n larger than or equal to 1. So we have just a problem in n equals 0. Just one problem, finite number of problems. This is a sequence. If we consider bn equal to 1 divided by n minus 2024, well, this is defined for example, can be defined for n larger than or equal to 2025. So that implies that the only problem that we have is for n equal to 2024. So again, a finite number of problems. If we have Cn equal to the square root of n minus 2024, well, this is defined for n larger than or equal 2024. So we have problems for n from 0 to 2023. Again, a finite number of problems. And if we have dn equal to the square root of 2024 raised to the 2024 minus n, well, this is not a sequence, because we have infinitely many problems in its definition, namely all n larger than 20, 24 raised to the 20, 24. There are infinitely many possibilities, values of n, such that these difference is less than 0, so we cannot extract the square root. So in this case, this is not a sequence because we have infinitely many problems. Right, okay, so let's make now another observation regarding the difference between definitively and frequently. Okay, if we say, for example, that P of n is definitively true, we know that that implies that after some value n0, P of n is always true. And let's suppose that we want to negate this proposition. We want to negate the fact that P of n is true beyond some value n0. So that implies that there must be infinitely many values of n that make P of n false, which is to say that basically the predicate P of n is false for infinitely many values, or if you want, we can also say that P of n is false frequently. Okay? Keep in mind this because we will be using at some point this observation. Let's now move to the visual representation of a sequence. How can we represent a sequence of numbers? Well, there are fundamentally three ways of doing this. The first one is the Cartesian way, which basically consists in the plot of plot in the x, y plane of the points n, a, n. For example, let's consider the sequence an equal to 1 over n, and we know that this is defined for n larger than or equal to 1. Well, we can plot this. Let's say that this is 1, this is 2, and this is 3. We would like to represent the point 1, a1, and the point 1, a1, of course, because we know that a1 is equal to 1 over 1 is equal to 1. So this gives rise to the first point, which is 1, 1. Then because a2 is equal to 1 over 2, and so this gives the point 2, 1, 2. A3 is equal to 1 divided by 3, so this gives the point 3, 1/3. So what we need is basically representing this first point 1, 1, then we have, if this is 1/2, we have the point 1, 2, 1/2, then there will be 1/3 here. Yeah, so this, we have this point. So this is the point that corresponds to A1. This is the point that corresponds to A2, and this is the point that corresponds to A3. The second way of representing a sequence is on a line. Which means plotting the points AN on a line. So if this is the real line, this is the origin, the sequence AN will start from, will take values 1, 1/2, 1/3. So we can just plot the sequence in this way, saying that this is A1, this is A2, this is A3, and so on and so forth. So we are just identifying points on the line that represent the real numbers, which are the images of natural numbers according to the sequence. We have a third way of thinking about a sequence, which is by using the idea of bulbs. Now, let's think of a line with bulbs on it. These bulbs, they are switched on at every second, and they are switched off after 1 second. Let me explain this with an example. Okay, so let's suppose that we have our timeline. Okay, so the time, we have a clock that is counting all the seconds. Okay, so we have second 1, second 2, second 3, second 4. So this is the time that goes on. We would like to represent what is the image of n equal 1. Okay, we know that this will be A1. Okay, so we can think that there is a line where at some we have A1 here, which is the real number corresponding to the real natural number 1. Okay, and when the time comes that t is equal to 1, we will switch on A1, this bulb, and we will keep this alive for 1 second. Then times get to 2. Okay, so when times gets to 2, we have another point on the line that corresponds to A2, and that bulb, which is in A2, will be switched on for 1 second, which is the duration of the time between 2 and 3, and so on. So let's say that at some point after 1 second we will turn off A2, and then we will turn on A3. So that implies that in the second that goes from 3 to 4, we will keep only A3 open. So every bulb is switched on when the time corresponding to the natural number is reached. Okay, so that's the idea. We will be using this idea when defining limits, which is the next concept that we are introducing. This is a crucial concept. So let's now give the definition of limit of a sequence. Let an be a sequence of real numbers and we are referring now to the common definition, which is the less stiff definition, so that basically we can define the sequence as long as in the definition we just have a finite number of problems. Okay, we will be referring from now on to the common definition of sequence. We can say that there are only 4 possible behaviors of the sequence. Behavior 1, the sequence will tend to a real number L. This thing can also be expressed by saying that the limit of an for n that goes to infinity is equal to L. And in this case we say that the sequence is convergent. Second case, an will tend to plus infinity, which can also be expressed as saying that the limit of an for n that goes to infinity is equal to plus infinity. And we say that the sequence is divergent. Case 3, an tends to minus infinity, which can also be expressed as saying that the limit of an for n that goes to infinity is equal to minus infinity, and this is another case of divergent sequence. Case 4 is that an has no limit. In other words, there is no limit of an for n that tends to infinity. And in this case we say that the sequence is undeterminate. Good. Now we need to characterize each of these behaviors. Okay, we will give a definition for each of these behaviors, and we'll start from the last one. Okay, because the last one is the simplest. The definition of the case 4, the fact that the sequence has no limit, is quite simple because it is none of the above, which is to say, if a sequence does not satisfy case 1, case 2, or case 3, it falls into case 4, which means that the sequence has no limit. Okay, let's now pass to the definition of the case 2, which is the one where basically an diverges to plus infinity. Okay, we can brutally express this behavior in this way. When you see the green pen, it means that I'm trying to brutally express the concept. Then we'll give a formal definition of it. Okay, we can say that an is exceeding definitively any positive barrier, which is to say that whatever large positive number we can think of, at some point the sequence will go beyond that barrier, will exceed that number. Okay, let's now give the formal definition of this. we say that for every m real number, an, the sequence, is larger than or equal m definitively. So this is the definition of divergence to plus infinity. For every possible number, and notice that when we say m, this can be a very large positive number. Okay, so this can be a very large positive number. So whatever number you may think of, m, I can always find an element of the sequence that will exceed that number. So suppose that you give me m, then I will find you an element of the sequence an that is larger than m. Okay, then you come back and give me another value of m, then I will find you a new value an which will be larger than m. So this is just a two-player game. If I can play this game, I can say that an is divergent to plus infinity. There is also an alternative definition to this. Okay, the alternative definition that we can use is the following. We can say that for every m real number, there exists a natural number n0 such that for every natural number n larger than or equal of n0, an is larger than or equal to m. So this is basically expressing the same concept, but the thing is that now instead of having a different n, I will be identifying basically a value n0 such that beyond that value, for every possible n beyond that values, the corresponding an will be larger than m. Okay, and of course let's make an observation here. In general, n0 depends on m in the sense that the larger m, the larger n0. Okay, so we have now the definition for case 2. Let's go now to the definition for case 3, which is very similar to this one. So definition of 3. And we can say, let's try to give the brutal description of this. We can say that an is preceding definitively any negative barrier. So this is just the opposite of the case 2 in the sense that now we are playing a game where you give me a very negative number m and I can find you an element of the sequence which sits to the left, which is less than m. Then you come back in this game with a new m, even more negative, and then I can always find you a new element of the sequence which is to the left of m. Okay, so formal definition of this is the following. We can say that for every m into the real numbers, an is less than or equal to m definitively. So this is the formal definition, and notice that this value of m that we are considering now, this value of m can be a very negative number, and this basically gives the idea of divergence to minus infinity. Okay, last but not least, let's give now the definition for the case 1. Definition of case 1. Remember, the case 1 is the case where basically an tends to a real number L. Okay, now the brutal idea behind this definition is the following. We can say that in the long run, the bulbs that are switched on are close to the real number L. Okay, so let's translate now this idea into, let's visualize this idea. Let's suppose that we have L here. We are saying that after a while all the element of the sequence will accumulate close to this L. Okay, we need to translate now this idea of accumulation close to L, and what we say is that basically we can think that all the bulbs corresponding to elements of the sequence after a given n0, they are very close to L. Okay, now we need to formalize this idea, and we can formalize this as follows. We can say that for every epsilon larger than 0, now we can think of any possible small positive number epsilon larger than 0. We can say that the elements of the sequence will be in this interval between L minus epsilon and L plus epsilon definitively. So this is the formal definition of convergent sequence. So whatever epsilon you may think of, we know that the elements of the sequence after a while, okay, definitively, remember what definitively means, okay, it means that after some value of n0, we know that all the sequence will be in this interval between L minus epsilon and L plus epsilon. So I can always find you an element of the sequence that will belong to this interval. So this is to say that you can propose an epsilon, a very small epsilon. Well, then I will find you a barrier in the natural numbers such that beyond that barrier the corresponding elements of the sequence will be just between L minus epsilon and L plus epsilon. So let's give an observation. Let's make an observation on this. We can say that intuitively the closer is epsilon to 0, the larger is n0, right? So in other words, we can before giving this observation, let's try to give an alternative definition, okay? An alternative definition for the convergence of a sequence, we can say that basically for every epsilon larger than 0, the distance between an and L, okay, which is basically this distance. The distance between an and L, this distance. Now we can represent this distance with an absolute value. Remember that we are dealing with real numbers, so we take the difference and we take the absolute value. We have basically always a positive number, the distance. This must be less than or equal to epsilon definitively. Okay, so this is an alternative definition. Now, if we use this alternative definition, we can understand our observation maybe a little bit better, because we say that clearly the closer is epsilon to 0, which means the smaller is epsilon as a positive real number, the longer is gonna be the larger is gonna be n0. So I need to wait a little bit longer in order to see all the elements of the sequence accumulating around L. Okay, the closer is the distance from L that you want to have, the longer I have to wait. Right, so let me then finally observe that this represents the distance between an and L. Good. There is also another definition that we can give regarding a convergent sequence, and so we have another alternative definition. Instead of giving just the convergence to a number L, we want to specify now in which way are we getting closer and closer to L. Okay, so we can define a right limit and a left limit. Okay, so the right limit basically is saying that an will tend to L plus, okay, or we say that an tend to L from the right, and the definition is for every epsilon larger than 0, we can check that an is between L and L plus epsilon definitively. So what we are saying that is that if we once again try to visualize this process, what we see is that we have L, this is the real number, this is the real limit, and we'll see that for every epsilon you give me, I can find you an element of the sequence in this interval, an. However, this element will never get to L, will be always to the right of L. Okay, so in fact, it is important to notice that this, to have a right limit, this must be a strict inequality. Okay, so this is just one way of representing the fact that the sequence is tending, is approaching the value L from the right. Similarly, we can define the left limit as follows. We can say that, we can say that I don't know why this is not working now. Yeah, we can say that an tends to L minus if for every epsilon larger than 0, an will be between L minus epsilon and L, and this has to be true definitively. So this is a very similar definition of the left limit, and the representation of this, the visualization of this, is quite intuitive, because now if we have L, whatever epsilon you may think of, we know that definitively we can always have an element of the sequence which will be to the left, and again an can never achieve L. Okay, so it is important to notice that also in this case this must be a strict inequality, okay, for the definition to be true. Okay, so it's time now to see a few examples of sequences and try to apply all the concepts that we have introduced. Okay, so let's see a few examples, and let's start with an equal to n squared plus 3. Well, it is easy to see that an will diverge to plus infinity. In fact, if let's change color. If m is equal to 10 to the 6, then I can pick n0 equal to 10 to the third, and for every n larger than or equal to n0, the condition of the divergence to plus infinity is verified. If you come back and say, okay, but I want to have a new barrier, m equal 10 to the 12, then I can pick n0 equal to 10 to the 6, and so on and so forth. So this clearly verifies the condition for divergence to plus infinity. Let's consider a new example. Let's consider an, or let's call this bn equal to 1 over n. Well, clearly bn tends to 0, because we see that as n gets larger and larger, bn gets smaller and smaller. But we can say even more than this. We can say that bn tends to 0 plus, because bn will be always positive, will be always sitting to the right of 0. Third example, cn equal to minus 1 to the n. Well, this sequence now is taking minus 1 plus 1 minus 1 plus 1. These are all possible values, okay? And we see that this sequence never gets too close to anything. So clearly this sequence has no limit. So we are falling into the case 4. Now, let's point out something. Let's call this beware of intuition. There are some pitfalls, okay, when evaluating limits. One might be tempted to fall in one of these traps, so it's good to point out a few of these possible traps. Let's consider, for example, the a sequence Pn equal to let's consider a sequence Pn that goes to plus infinity. Okay, one might be tempted to say that because Pn goes to plus infinity, Pn must be definitively increasing, right? Well, that seems intuitive, right? So if Pn will go to plus infinity, will divert to plus infinity, I would expect that this sequence is always increasing, or at least is increasing from some n0 onwards. Well, this is totally false. Okay, so this is false. And I will prove this with an example. Let's consider the following sequence. The behavior of this sequence is a reminder of the story of Penelope in the Odyssey. Penelope was Odysseus' wife, and she wanted to remain faithful to his husband, Odysseus, and basically she promised that she could marry someone else when she had finished weaving a burial shroud for Odysseus' elderly father. But every night for 3 years she undoes part of the shroud, so basically she will never finish the shroud itself. So if we look at this behavior in this the behavior of this sequence, we see that clearly this sequence can go beyond any possible barrier we can think of. For example, if we give a barrier m as large as we like, at some point the sequence will go beyond that. But we cannot say that this is definitely increasing. In fact, there will be always decreasing parts of the sequence. Okay, so this was a first pitfall. Another example where intuition may be dangerous is the fact that, let's suppose that we have a sequence that will converge to 0. We might be tempted to say that then an is going to 0 plus, or an goes to 0 minus. Okay, well, even this is a false conclusion. And in fact, we will prove now with a few examples that this is not the case. For example, let's take this sequence: 1 minus 1/2 plus 1/3 minus 1/4 plus 1/5, and so on and so forth. What is the general term of the sequence? We can say that this is minus 1 to the n divided by n plus 1. In fact, in the first case, basically if we apply this with the 1, we have, let me change the color. Let me use this color here. In this case, we have minus 1 to the 1 to the 0. This is the term a0 clearly, divided by 0 plus 1. Okay, so this is a0. This will be a1, and in fact this gives minus 1 to the 1 divided by 1 plus 1, and so on and so forth. Okay, now clearly we have a sequence that tends to 0. However, this sequence is taking positive and negative values, so it will have a behavior like this. It will tend to 0 from both sides, so you cannot say that this is tending to 0 plus or to 0 minus. Okay, another pitfall might be the following. Let's consider an example 6. We might think that if an goes to 0 plus, an is definitively decreasing, right? But this is another false conclusion. As an example of that, let's consider just the inverse of the sequence Pn we have considered in case 4. Okay, I'm considering just the inverse of this sequence Pn. You remember this sequence, right? We are taking the inverse of each and every element except the first one. Okay, well, if we take the inverse of this, we get the following sequence: 1, 1/2, then we have 1 again, then 1/3, 1/2, and then 1/4, and again. So we clearly have that 1 over Pn is converging to 0 plus because all these are positive numbers, but we don't have a decreasing sequence because we always have small steps where the sequence is increasing. Final example, example 7. If the supremum of this set, the following set, the set of all possible values that an takes when n is in the natural number, so the supremum of all possible values of the sequence, if this is plus infinity, right, we might be tempted to say that, oh, okay, then that means that an is divergent plus infinity. Well, this is another false conclusion. Sorry. False. And in fact, just as an example of this, let's consider the sequence 0, 1, 0, 2, 0, 3, 0, 4, and so on and so forth. Well, clearly, this has no limit. Still, the